Okay, so let's do problem 6 and 7. Write the equilibrium expression for this reaction, and then another one for this one, and then this is the backwards where you have the equilibrium equation and you have to write the reaction for it. All right, so I'll give you guys a little bit of time. If you would let me know just in the chat room when you guys are ready, and we can go over it. Okay, so let's go over this. Okay, so remember these expressions, these equilibrium constants, either K or KEQ, you might see it either way in the text, they just do Ks. It's the concentration of your products divided by the concentration of your reactants. All right, and then depending on the balanced equation, whatever number you have, you put it as an exponent up here. All right, so for the first one, the KEQ of the first one, we'll write it in here. It's equal to the concentration of CO2, and since there's a 2 in the balanced equation, you square it. And then divide it by CO squared times the concentration of oxygen. So that would be the KEQ. Make sure you multiply it. A lot of people sometimes, I've seen this in the past, they just assume it's plus because there's a plus there, so they do CO2 squared plus O2. It's not, it's times. Make sure you multiply everything. Okay, so that would be the KEQ for that expression. Any questions? No. And then for this one, you would have CO2 up to the 4th power times H2O to the 4th power divided by C2H6, which is ethane, to the squared times oxygen to the 7th power. Okay? And then write the chemical equations. Well, it's the backwards of this, right? So remember the products is on top, the reactants are on the bottom. So you would have CH4 plus 2 O2s give you, and you would draw the equilibrium arrow. Shouldn't H2O be to the 6th power? Yeah, I'm sorry. Yes, thank you. Yeah, thank you. And then, let's see, this would be CO2 plus 2 H2Os. All right. And then for the ozone one, you would have 2 O3s yield 3 O2s. Should be pretty straightforward. Make sense? Any questions? All right, and then for the next one, now let's actually do a problem with numbers, and then we'll analyze the number, the KEQ you actually get, and you'll tell me if which side of the reaction it favors. Right, so we kind of talked about that, depending on if K is less than 1 or is greater than 1. Okay? So go ahead and do this one. So what is the actual value? What is K? So you have to do the equilibrium constant. You got to plug in the numbers, figure it out, and then tell me which side of the reaction it favors, understanding what that number is telling you. All right, let's start back. Most of you are done. So the equilibrium constant, let's do that first. So the KEQ will be the amount of NO squared times Cl2 divided by NaCl squared. So that would be 0.92 squared times 0.20 divided by 1.31 squared. Get my calculator. So 0.92 squared times 0.2 divided by 1.31 squared. And I get 0.0, let's see how many sig figs. 2 sig figs. 99. Is that what you guys get? Making sure we're all, I know. Yeah, okay. Okay, so what is favored, reactants or products? Remember it, K, remember, is equal to the products divided by the reactants. So in math, if this is greater than 1, that means my product side is greater than my reactant side. Right? It means my top number is larger than the bottom number, which gives it greater than 1. If this is less than 1, that means my R, my reactants, are greater than my products. That means that the denominator is a bigger number. So that means R is really big and the product side is very small. That would give me a less than 1 value. So that would imply that the reactant side is favored. So since this is way less than 1, I mean this is 0.1, that means that the reactants are favored. This side of the equation is favored. That means I have a lot more of this. I have 10 times more of this, or 9.9 times more of this than I do of this. So that means that the reactant side is favored. How does this relate to the K value? So I just told you, if it's less than 1, it's the reactant side. If it's greater than 1, it's the product side. Okay, there also is no unit for this. So it's just a number. It's just kind of telling you how many more times one side of the equation is favored over the other side of the equation. All right. Yeah, so it's 10 times. Yep. Okay, everybody get that? Does that make sense? So if you understand how to do this, and you'll have no problem on these questions and understand what the number means. So it's writing the KEQ, it's being able to put the numbers in and get a number, and then understanding what that number tells you. Also understanding what equilibrium is, but I'm feeling you guys got that. All right? Okay. Clear this. So that's KEQ stuff. And then the last thing is doing Le Chatelier's principle. Okay, so remember that's how to change an equilibrium, how to alter an equilibrium. Last week we talked about the Haber process and what that was all about. I'm going to delete this about the volume because I told you guys don't worry about the volume part of it, so you don't have to answer that question. Okay. So based on this equation, I got heat plus NO2 plus H2O gives you oxygen and ammonia. Tell me which way the equilibrium will shift based on what I do. So if I add heat, which way will it shift? Left, right, or have no change? If I add NO2 or if I remove ammonia. All right, so I'll give you guys a little time. Let me know when you guys are ready, and we'll do that one. I think you got it. I bet you guys have got it. Okay, so remember this is like the seesaw approach. Okay, if you increase any particular side, if any side increases, all right, you want to remove that excess that has increased. So if we have a seesaw, all right, here's like the fulcrum, and let's say you increase the concentration of the reactants. So here is the reactant side, it's the left side of the equation. Here's the product side. All right, you always want to get it balanced at the end, equilibrium. That's supposed to be a straight line, by the way, guys. I'll do my best to get it straight. Okay, so if this side is higher, this needs to come down in order to get equal, and the product side needs to go up. Okay, so if I'm increasing the reactant side, these reactants have to react and start forming more product. Okay, so by forming more product, the reaction is going towards the product side. Okay, so if we add heat, so I'm increasing the heat here, so I'm in this kind of a scenario, the reaction I have to get rid of this excess heat. By doing that, this has to react to start forming more of my product. So by adding heat, the equilibrium shifts towards the product side. Okay, the product side. Or you can say it shifts towards the right. All right, I don't know what the multiple choice questions will say, but as long as you understand both, it shifts towards the product side. Oh, you know what? I need my pen. I'm not doing it with the mouse. Product side, or it shifts to the right. It just all depends on how the multiple choice questions ask you. But it'll say which way does the equilibrium shift. All right, does that make sense? So if your reactant's going up, you got to shift this way in order to bring this back up and to bring that down in order to have an equal. All right, if I add NO2, so I'm adding NO2, same thing. I'm in this kind of a scenario. So the equilibrium is going to shift to the right, or the right. Let's put lowercase so we don't confuse it. The right, or you can say the product side. If you remove ammonia, so this time the ammonia is going down. So again, we're in the same kind of a scenario. My product side is lower than what it was originally in equilibrium. So again, in order to, I have a hole. It's basically the ammonia is gone. So I have to shift towards the right to fill back up that empty spot of ammonia. So again, this is towards the right, or the product side. Okay, everybody get that? So in this case, it's product for all of them. Good, yep, good. Good. All right, that's pretty much it for the chapter. I think that's really all we've really talked about for this chapter. So any questions on that? You guys feel pretty comfortable? It seems like you guys pretty much got it. It's not hard. It's pretty straightforward. All right, good. All right, let's start going over these. We have about 10 minutes left. So, show the reactions, show the conjugate acid and base. All right, so in this case, this is obviously our acid, because it's nitric acid. And this water, in this case, is going to act as base. Remember, water can act as both. All right, so the proton is going to transfer from the nitrate onto the water. All right, to give me H3O with a plus charge, because the H and the plus travel over there. And then the nitrate is going to be left with a minus charge. So that's going to be your conjugate acid-base pair. This will be the conjugate base, and this will be the conjugate acid. Because remember, whatever the water is here, it's the exact opposite on the other side. Whatever the nitrate is part of here, it's the opposite on that side. Or just look at the reaction in reverse. The nitrate is accepting a hydrogen to form HNO3, so that makes that the base. All right. For this one, there's two possible answers. You don't know. So we know water is an acid or a base. And in this case, you don't know. Is this acting as the acid or is it acting as the base? So there are two possible answers in this case. One case is where the H is given to the water. So this would be acting as the acid and this would be the base. And you get CO3 with a 2 minus charge. H2O plus. However, you can do it the other way. The water can give it to the carbonate. And in that case, the water would be acting as the acid, and the bicarbonate would be acting as a base, and then your products in this case would be H2CO3 plus OH minus. All right, so this would be the conjugate acid in this case. This is the conjugate base. In this case, this would be the conjugate acid, and this would be the conjugate base. So in a case like this, you don't know. In this case, it's obvious. You can't accept the hydrogen. That is nitric acid. You can't put an extra hydrogen on nitric acid because it's a neutral charge. Since this is a minus charge, we can either lose a hydrogen or we can gain a hydrogen. We can do both in this case. But in this case, you can't. Okay? This was a little confusing. Practice these. It takes practice in order to do these. Okay, and that practice sheet I gave you, you definitely have more problems. So you have 2 more here. Plus you have these, which will, so, if you have HNO2 minus, what's the conjugate acid form of that? Add an H plus to it and show me what that formula is. Okay, so there's more practice. Okay, will it matter then what we put for the answer on the second one? No, in this case it won't. On the exam, it'll be very clear as to which one. I just want to make sure that you understand that it could be both. The question would be like, what's the conjugate acid base, assuming water is acting as the base? So then it's got to be that one. If they say assuming water is acting as the acid, then you would know. All right, or more likely it'd be a problem like A, where there is only one possible answer. Okay, so the one down here, the first thing you need to do is write a balanced equation. If you don't write a balanced equation, you don't know what how many moles of everything there is. So you got to first write a balanced equation, and you'll find out you have 2 HIs plus CdOH2, cadmium hydroxide, forms 2 H2Os plus, I believe, CdI2. Okay, so it's a 2-to-1 ratio. You need to know that because when you're converting to moles, you got to make sure you do the mole-to-mole conversion. Okay, so we're trying to find the molarity of HI. We're trying to find the molarity of this. Okay, we're given the volume of it. So remember, molarity is equal to moles over liter. I'm given the volume. The volume is 0.125 liters. So I need to find the number of moles of HI. I'm given information about CdOH2. So I'm given all the information of CdOH2 that I hit the equivalence point to figure out the moles of HI. And remember, however many moles of CdOH2, that's going to equal the number of moles of HI. Okay? So I take the volume of CdOH2 and the molarity. Remember, if you're given a volume and a molarity, you can always find moles. 5 moles. I'll put CD rather than writing the hydroxide the whole time. So that's moles. I'm sorry, that's liters, not moles. That should be liters. And then we're given 0.209 moles of CD over 1 liter of CD. Right? So the liters of CD cancels with liters of CD. This will give me moles of CD, but what do I want? I want moles of HI. So I know that for every mole of CD hydroxide, there are 2 moles of H+. I'm sorry, of HI. So when I do this, I will get, what is it, 0.033, is that 25? Try to get as many sig figs as, I think, 25 moles of HI. So I just found my moles of HI. I now need to divide it by the volume, which is 0.125 liters. And when you do that, you get 0.266 molar of HI. That's going to be your answer. Did you guys get that? Make sure. Yep, okay. Good home.
I'm kind of confused at the equation. Why is it the 0.209 mole?
Because what does molarity mean? What does capital M mean?
Moles over liter?
Moles over liter. So it's 0.209 moles over 1 liter. That's what that means right there. That's what a molarity means. It means moles over liter. So 0.209 moles over 1 liter, which is what that is right there. That's the molarity.
I would just think you'd need to solve for mole because the 0.209 is the molarity.
Yes. So the molarity of the cadmium hydroxide is 0.209. Right. Yeah. So, and I need to find moles of HI. That's what I'm looking for as of right now. I'm looking for moles of HI. So if I'm given this many liters, and that's the molarity, I can find out how many moles of CD there is. Okay. So I multiply them. Another way of doing it is, molarity equals moles over liter. So if I want to find the number of moles, I bring liters over. So it's liters times molarity equals moles, right? Which is basically what this is. Liters times the molarity equals moles. I'm just doing it in equation in a dimensional analysis form rather than in the equation form.
Okay.
All right. And then since it's a 2-to-1 ratio, if it was a 1-to-1 ratio, I wouldn't have to worry about it. But since it's a 2-to-1 ratio, I got to make sure I do my mole-to-mole conversion in this case and convert it to moles of HI. All right. All right. Do that. All right. Let's do the last problem. With to kind of speed things up here a little bit. Let me just delete all this. Okay. The last problem is I'm looking for the pH. I got to find the pH. Remember, the pH is equal to the negative log of the H plus ion concentration, right? Well, I give you the hydroxide ion concentration. I don't give you the H plus concentration. So I have to find the H plus concentration using the hydroxide concentration. So if you remember the other equations, so there were 3 equations associated with these types of problems. So there's this equation where concentration of H plus times OH minus equals this number. So I'm going to use this to find the H plus ion concentration by plugging that number into there and solving for H plus. And then once I have H plus, I then can plug it into there. All right, so this is equal 1.00 times 10 to the negative 14th divided by 1.12 times 10 to the negative 4th, which I get 8.93 times 10 to the negative 11th. All right, just double check to make sure that's right. Remember, when you do division of exponents, you subtract them. And when you subtract them, that's roughly what that number should equal. So it should be about minus 10, but because I have all these other numbers here, it's at minus 11. As long as you don't have minus 18, that means that you have added them and you have done the wrong calculation. All right, just remember this number should be an approximate plus or minus 1 of the subtraction of these two numbers. All right, so now this is the H plus concentration, so I plugged it into the pH. Roughly, based off of just looking at this number, what should my answer be about? What should it be? We talked about how to look at what log means. Yeah, it should be about 11, right? It's basically whatever number that is, that's approximately what it should be, plus or minus 1. So it's either 10 or 11 or 12. It's somewhere around there. Okay? So now you actually do it. Take the negative log. All right, I would not just answer it like that. However, on a multiple choice question, let's say that you got this far and the answers were 2, 6, 8, or 10. You don't even have to do the calculation. You already know what the answer is. What's the answer? It's 10. Exactly. So that's kind of a strategy or tricks in doing multiple choice questions. If you roughly know what the answer is prior to doing any more math, you don't have to go any further, right? In a multiple choice, if I have these, now obviously if I had like 10, 10.5, 11, and 11.5, well, now you kind of have to do it because it could be possibly any one of these 4. But if it was so obvious like that, then you don't have to go any further. So that's also another way of how to speed up in multiple choice questions. So if you're doing a big, lengthy problem like this, and you get to this point, and the answers are 2, 6, you can save yourself a step, and you don't have to do this. You know it's roughly around 11. All right? But when you actually do it, I think the answer is 10. I think you actually get like 10.0 as the answer. Okay? So that's kind of a trick in doing multiple choice questions. I remember when I had to take the GRE, that was one of the major tricks that I learned. I was like, man, I wish I learned that in high school. That would have saved a lot of time in a lot of cases. But it's that one trick that some people learn, some people don't until later. I learned it after it was done in college already. I was like, I wish I knew that. That would have saved some time on some exams. Okay. All right. Okay. We are a little bit over time, so I will tomorrow. I'll see you guys tomorrow. Please come. Just ask questions. If we don't have anything to talk about, then I will just kind of possibly see you on Thursday. Otherwise, good luck to you guys. Yep, no problem, Kaylin.